For part A of this problem, we will use the find displacement law. Which says that the wavelength times the temperature is constant at 2.90 times 10 to the negative third meter Kelvin. So the wavelength itself is going to be 2.90 10 to the minus third meter Kelvin over the temperature. And we're told that the temperature is about 5800, 2.9 10 to the negative 3 meter Kelvin over 5800 kelvins. That will give us a wavelength of about 0.5 times 10 to the negative 6 meters, which is the same as 500 nanometers. And for part B, we can use the Stefan-Boltzmann law. Which says that the intensity is equal to the Stefan-Boltzmann constant times the temperature to the fourth power. The Stefan-Boltzmann constant is 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth, and the temperature is 5800 kelvins all to the fourth power, which gives us 6.42 times 10 to the seventh watt per meter squared, or 64.2 megawatt per meter squared. For part C, we can use the equation for intensity for the Planck radiation law. Which says that I, as a function of lambda, equals 2 pi hc squared over lambda to the fifth times e raised to the ec over lambda kt minus 1. This is going to be too much to plug all the numbers, so let's start by finding what hc over lambda kt equals. So h is 6.626 10 to the minus 34 joules second. C is 3 times 10 to the 8th meters per second. The wavelength of the average range is 6.025 times 10 to the negative 7 meters, which is the 602.5 nanometers, the average of the two wavelengths given, times the Boltzmann's constant of 1.381 times 10 to the minus 23rd joule per Kelvin times the temperature of 5800 kelvins, and this gives us a value of 4.116. That means that high lambda is going to equal 2 pi h, which is 6.626 4 joules second times the speed of light squared over lambda, again, is the average of the two wavelengths. Times e to the 4.116 minus 1, and this gives us an intensity of 7.81 times 10 to the 13th watts per meter squared. And you notice that the intensity in the 5 nanometer range between the 600 to 605 nanometers is then approximated by I lambda times delta lambda, which is going to be the 7.81 times 10 to the 13th watts per meter squared times the difference between our wavelengths is 5 nanometers, and this gives us an intensity change of 3.9 times 10 to the 5th watts per meter squared, or 0.39 megawatt per meter squared.